Hey guys, I decided today, I had a couple of you send me some questions about this homework assignment down below, and I decided to kind of do some Chemoramma stuff outside of school. So there are going to be some videos on my YouTube channel that are just based on questions you guys have asked me or things you need help on. So just to make sure that we're all on the same page, I did start a new class kick. Here's the code. You might want to screenshot it right now so you have it. And once you screenshot that, you can enter this code into ClassKick and you can get all this information. You might be able to get it now, but I'm going to be kind of scrolling and talking and everything else. So just go on ClassKick and grab it. Also, remember, my email address is, let's see if I can write it. My email address is adanell, ADAENELL, at eacs.k12.in.us. And if you have questions about anything related to chemistry, whether it's my assignment, somebody else's assignment, it doesn't really matter. I just want you guys to understand. So if you guys email me or remind me questions like this assignment down here, I can kind of give you a quick overview and get you back on track. You can also ask Mr. Tonkel. He is also very much available for help. So don't be afraid to ask him because he'll help you too. So this video is going to kind of get you up to speed on these questions down here. I have to kind of talk about some previous information that you guys probably covered, I'd say probably before spring break, just to make sure that you can do these problems down here. Please do not fast forward through this part because the bottom part is not going to make any sense if you fast forward through it. So here we go. Once upon a time, there were some scientists. Let's zoom in on this picture. There were some scientists. There were actually 3 of them. And their last names were Boyles, Charles, and Gay-Lussac. Okay, so that was their last name. And they were this really awesome group of scientists. Got to pick a better color. Pink. Okay. They were this awesome group of scientists where they were like, hey, guys, why don't we study gases? And they were like, yeah, let's study gases. It's going to be so much fun. Okay, so they started by looking at, let's just draw a little picture up here, the molecules in each state of matter. They were like, okay, we know we have solids, liquids, and gases. And the particles of a solid are like all close together and all lined up, and class kick is not cooperating, and they're all perfectly spaced out and all lined up, and they don't move very fast. Now, particles of a liquid, there's a little bit more space between them, and they kind of like slide past each other when they move, and liquids flow. And then you have gases, and gases are like a bunch of kindergartners who had a whole bunch of pixie sticks, and then we let them run around the gym. And they're just crazy everywhere, all over. So these 3 scientists were like, okay, solids, check. We understand them. They work so good. They're polite. They stay organized. Liquids, yep, got them down too. Pretty organized, but we can deal with that. And they were like, gases? Oh man, I don't know. So these 3 scientists were like, well, let's come up with some equations to describe the behavior of gases. And that's how this whole thing started over here. Now, Boyles, Charles, and Gay-Lussac have laws that I'm going to talk about in just a second. And they are laws that go with pressure, volume, and temperature because those are the variables we use to describe a gas. So when you're doing any of these equations over here, and this whole chapter is just math and equations and algebra, that's all it is. So whenever you're doing any of these, you're looking for these variables. So the variables we use to describe a gas, all these crazy particles being all crazy, good thing they're not in quarantine, okay, being all crazy, all these particles are described using these variables. Now, see how it says pressure is represented by a P and that's in kilopascals? Well, kilopascals is like the abbreviation is KPA. So if you see like 107.3 kPa, what is that? Up, it has kPa behind it, therefore it is a pressure. That's how you know. Okay, let's get rid of all this stuff. I got kind of carried away. Okay, surprise, right? No. Okay. All right. Then we also have volume, and that is measured in liters. So again, if you see some random number like XXX point YYY, and then it has an L at that behind it, that's liters, so therefore it's a volume. Now, temperature has to be measured in Kelvin. So if you see a K behind a number, it's a temperature. And then N is the number of moles. I don't know why they decided that, but they went with N to represent the number of moles. So that one's a little bit tricky because you're like 103 moles. Guess what that is? It's moles. It's N is your variable. So that's kind of just a quick rundown. And if you know these variables and you know these units right here, it makes it really easy to look through a problem and just throw out all the unnecessary words and focus in on what you are trying to find. I grabbed a couple slides from my notes. If you look right here, see how it says chemistry, or it says chapter 14 chem PDF. That is on my Canvas page. It's Canvas Files Unfiled. If you are part of my Canvas, you can access all of the notes on there. And if you are not part of my Canvas page because you're not in my class, just shoot me a quick email and I will add you in my Canvas class. And then you have access to every chapter of notes for the rest of the school year. And I don't know, if you want to use them later, that's cool too. Okay, so really quick, I know I'm talking fast. I'm just trying to make this video not like 2 hours. So it's not going to be 2 hours. I'm just kidding. Okay, so let's talk about the super cool 3 scientists. So they figured out some variables that they were going to track based on their fun-filled quest to learn stuff about gases. And they looked at gas pressure. Now, pressure is just a nice way to say push. Every time I read the word pressure, I actually change it to push. So if I say this, it says factors affecting gas pressure. I say factors affecting gas push. In other words, gases, even though they're just these crazy particles moving all around, they push on stuff. Like if you put, and you know this because you've seen this before. Okay, so here's going to be some awesome artwork. Okay, here is a tire. We can make it a car tire. I don't care. It looks like a donut, but whatever. Okay. If the tire is flat, what do? We put air in it. How does the air inflate the tire? Well, all these little air particles, they push out on the rubber that the tire is made out of, and then it's not flat anymore. So these are factors that affect how much a gas pushes on something. So look at this. Amount of the gas. If there's more gas particles, if I have a container or a tire, let's say my tire has to be inflated to a certain pressure. But let's say I measure it out perfectly and I only put 2 gas particles in here. Is that enough push? Probably not. My tire's probably still flat. Okay, it's like a sad, it kind of looks like a sad face. It's probably still a flat tire. But if I put a whole bunch more particles in the tire, a whole bunch more air particles in the tire, then it pushes because it increases the pressure. So the more particles you have, the more pressure you have. That's what that says. So you know that. So more particles equals more pressure if you're talking about a gas. Now let's see what we're going to look at next. Oh, volume. Okay, remember we're talking about pressure. How is pressure affected with volume? So I drew some pistons down here. They're actually on my slide. You find pistons in your car engine. At least I think they're in your car engine, whatever. So the more a gas is compressed, in other words, okay, so these 1, 2, 3, 4, 5, 6 particles have this much space to run around in. If I decrease the volume, what happens to the pressure? So it's these same 6 particles, but they have less space. So now they collide or push on each other more often. So if I decrease the volume, what happens to the pressure? The pressure actually increases. Let's look at the next one. One more. I don't need those lines on there. Okay. Okay, let's look at temperature. I don't know if you have ever gotten like a birthday balloon, like a helium I don't even know what I'm drawing. If you've ever gotten a helium balloon and you go and you get a happy birthday helium balloon in the store, maybe it's winter outside, and in the store it looks like all perfect and it's a nice shiny balloon. But then you go and you take it to your car, and when you're outside, the balloon becomes like this shriveled up, whatever. Okay? It becomes all like shriveled up. So, how is pressure affected with temperature? So, if I decrease the temperature, what happens to the pressure? See, what happens is the particles actually start moving slower. So if I decrease the temperature, the pressure also goes down. Now, our scientists back up here, Boyles, Charles, and Gay-Lussac, came up with laws based on these variables. So, when I was in high school, my chemistry teacher, which was, his name was Mr. Crum, and he was absolutely amazing, and I still talk to him to this day. He taught me some ways to remember these laws. Now, he said that Boyle's law has to do with pressure and volume. Pressure and volume. Now, if I decrease the volume of something, what happens to the pressure? If you go back and look at this piston example right here, if you go back and look at this, remember if we said we decrease the volume, we increase the pressure. So that is actually Boyle's law. So my chemistry teacher taught me that backwards Boyle was very poor. So he used to say that all the time. Backwards Boyle was very poor. And what he meant by that was Boyle's law. And he said it was backwards because if volume goes down, what happens to pressure? It goes up. If volume goes up, what happens to pressure? It goes down. So in other words, backwards Boyle was very poor. His law has to do with volume and pressure. That's where very poor comes in. And he said that it is an inverse relationship. In other words, if one goes up, the other one goes down. Now, the mathematical expression that goes with Boyle's law is right here. So there's our equation. Look, backwards Boyle was very poor. Now, let's look at Charles' law. Charles' law says, you want to know what my chemistry teacher taught me for Charles' law? I'm assuming you're all saying yes. Okay. So, Charles' law, he taught me Chucky liked to watch TV. So, Chucky, meaning Charles, I don't know why he said Chucky, but it just stuck with me. So, Chucky liked to watch TV. So, Charles' law, I remember, has to do with temperature and volume. And it's not backwards Chucky, it's just regular Chucky. So, if the temperature of a gas increases, what happens to its volume? Increase. If the temperature of a gas goes down, what happens to its volume? It goes down as well. In other words, it's not an inverse relationship like Boyle's law. Now, thirdly, our third scientist was Gay-Lussac. And Gay-Lussac, I always say Gay-Lussac like toilet paper because it was the only thing I could think of. So, toilet paper. Toilet paper. So, his law or mathematical relationship has to do with temperature and pressure. Now, there's nothing backwards about this law either. If temperature goes down, pressure goes down. If temperature goes up, pressure goes up. Now, I got this chart for you guys so you can see the mathematical relationships between the three. Now, it's really cool because these guys were friends. In fact, maybe they really liked each other. I don't know. But later, they combined all their gas laws into one. And they didn't come up with a fancy name. They just called it the combined gas law. Combined, like we combined them all together. Now, if you memorize the combined gas law, let's say we had a Boyle's law problem. Now, in my head, I'm already saying it. I'm saying backwards Boyle was very poor. So if I look at the combined gas law and say backwards Boyle was very poor, I know that Boyle's law has to do with very, which would be volume, and P, which would be pressure. So if I memorize the combined gas law and I cover up the other variable that he's not talking about, look at that. I have Boyle's law. All done. I have the equation. Let's see if it works for the other ones. So I'm going to erase these. Okay, so Chucky likes to watch TV. So I have to keep the T and the V and cross out the P. Oh, look. Boom. Charles' law. Let's check and see if it works for Gay-Lussac's law. Gay-Lussac liked what? Toilet paper. That's right. So I'm going to cross out the V because he only liked toilet paper. Oh, look. There you go. So if you're going to memorize one, you should memorize that one. Now, we also have the ideal gas law, and that is PV equals nRT. Pressure, volume, N was the number of moles. R is something called the ideal gas constant. Now, constant means it's constantly the same number, always. So, R is 8.31 as long as your pressure is in kPa, your N is in moles, your volume is in liters, and your temperature is in Kelvin. So You know how pi is 3.14? Pi is a constant. R is also a constant. If I put 17 pi, you would multiply 17 times 3.14 blah blah blah. I don't know the rest of the numbers. So every time you see an R, you put in 8.31. It's a constant. It's like a normalizer. So I think I've caught you guys up enough to do, well, to start you on one of these problems down here. So if we look at these problems, we are going to use these steps to solve all of these problems and any other problems that use any of these equations, laws, combined gas law. You can use these steps to do all of these problems. Okay, so I'm going to make you a list of steps right here, but I don't love green, so I'm going back to pink. All right, look. Use these steps to do all of these problems, and then you can ask me if they're right, and I will check them for you. Or you can ask Mr. Tonkel. I'm sure he has the answer key, and he will also help you. Okay, so here's the steps. Number 1, read the problem. Number 2, underline the numbers. Trust me, just do it. Underline all the numbers. Number 3, for number 3, you should assign variables. Okay, so I'm going to, instead of saying variables, I'm going to say assign P, V, an N, or a T. So in other words, say whether it's a P, a V, an N, or a T. I'll show you how to do it in a minute. Number 4, pick an equation. And number 5, do math magic. It's my favorite. And number 6 is always units and significant figures. Okay, so if we look here, let's look at this problem. I got this problem from somebody that asked me, I don't know how to do any of these. Mrs. Donnell, can you help me? And I said, of course I can help you. So, if we look at our steps, it says read the problem. Fine, I'll read the problem. Number 2 says a, man, it's hard to see. I'm going to have to go find reading glasses. A 35.0 liter tank contains 7.0 moles of compressed air. If the tank inside, if the pressure inside the tank is 500.0 kPa, what is the temperature of the compressed gas? Okay. What's number 2 say? Underline the numbers. Fine. I'm going to underline some numbers. Okay. Here's a number. Here's a number. Here's a number. And there's no more numbers. Okay. Fine. Fine. No big deal. Now it says, number 3 says, assign P, V, N, or T. So remember, you remember this slide up here? If it's a P, it's a pressure. Or if it's in kilopascals, it's a pressure. If it's in liters, it's a volume. If it's in Kelvin, it's a temperature. And if it's in moles, it's obviously an N. So, let's go back and see what we have. 35.0 L. So that must be I can't hear you guys. What is it? Oh, that's right. It's a volume. Good job. Okay, so 7... yeah, I think it's the 7.0. Okay, so 7.0 moles is an N. That's right, it's an N. Because N is our number of moles. And then if the pressure inside the tank is 500, and then it has a kPa. kPa, I don't remember what that is. Oh, right, it's kilopascals. Look at that. Okay, so kPa is kilopascals, so that means it is a P for pressure. Okay, now here's the tricky part, but easy because you did your work. Number 4 says, pick an equation. So, I have a single V, an N, and a P. And if I look at this problem, at the very end it says, what is the temperature? So I'm looking for a T. So the variables I have are V, N, P, and T. Okay, I have to figure out an equation. Which equation up here has a P, V, N, and T in it? Because guys, guess what? There's only one that has all of those variables in it. I'll give you a second to look. Which one has a P, a V, an N, and a T in it? Okay, you said ideal gas law, and I agree. That is the only one that includes the variable N. But some of you are like saying, Mrs. Donnell, it has an R in it too. What is that? But remember, R is a constant. It is constantly 8.31, so I have the value for that. So I'm going to use the equation PV equals nRT. Oops. Pink. Okay, so I'm going to use PV equals nRT to solve this problem. Now my next step says math magic, and that means I'm going to fill my variables in this equation. Remember, your variables must be in kilopascals, moles, Kelvin, and liters. If they are not, you must convert them before you use this amazing equation. So here we go. P. Do I have a P? I do. It's 500.0 kPa. So 500.0 times the volume. Do I have volume? I do. It's right there. 35.0. Look at me go. Equals N. Do I have an N? I do. 7. And by the way, I'm assuming that's 7. I can't see the picture really well, but I'm assuming it's 7. If it's not 7, change it to whatever it really is. It might be 8, might be 9. I don't really know what that number is right there. Okay, so 7.00. Okay, I like parentheses. It just makes my life easier. If you don't like putting it, don't put it. I don't really care. Now, times R. What's R? Oh yeah, 8.31, because it's a constant, which means it's constantly the same number. And what is T? Wait, I don't have a number for T. Oh, look at that, because that's what I'm trying to solve for. Times T. So let's work this out. I have to solve for T. That's what I'm being asked for. So I'm grabbing my calculator, like for real, I really have my calculator in my hand. So 500 times 35 is a big number. It is 17500 equals 7 times 8.31 equals 58.17 times T. How do we fix this? Divide both sides by 58.17 to get T by itself. 58.17. So, with that being said, you have 175. I feel like that's not right. 500 times 35. Yeah, that's right. Okay. Divided by 58.17 equals. So, these cancel. So the answer, 300.8423 equals T. I'm trying to get rid of that little line. Okay, equals T. So that's what we have. What's our last step? Units and significant figures. What is the unit on T? Go back up here and look. Temperature must be in what? Oh yeah, Kelvin. Okay, so I know that my unit on this is going to be Kelvin, but I need to figure out significant figures. Your significant figures are based on the numbers you started with. So let's look at our original problem. 35.0 has 3 significant figures. 7.00 has 3 significant figures. And 500.0 has 1, 2, 3, 4 significant figures. We can't have the most, we can only have the least. So volume and number of moles both have 3. So I need to make my answer have 3. Now, I'm just going to tell you, I'm going to put this in scientific notation because my significant figures will be perfect. If you don't want to put it in scientific notation, another acceptable answer would be 301. Or you could say, because that's 3 significant figures, because if you just write 300, that's 1 significant figure, and that's wrong. Because you can't do that. But if you write it in scientific notation, watch this magic. I can go 3.00 times 10 to the, how many spaces did I move it? 2 times 10 to the second, and that's also 3 significant figures. So the acceptable answers for this problem would be 301 K for Kelvin, or 3.00 times 10 to the second K for Kelvin. So that is how you do these problems. If you do them this way and follow those steps, it's 385 bazillion times easier. This one right here, like I'm just looking ahead for you guys, trying to like see if you're going to have any roadblocks. This says how many grams of helium does, this is a volume, this is a pressure, this is the temperature. Now this is a tricky problem because it's asking for grams. So what you need to do is solve for N, which is the number of moles, and then use your mole map to convert your moles to grams. And it says of helium. So you're literally going to take whatever moles you get from this problem and then convert it to grams. Number 4, calculate the volume. Ooh, STP, that's standard temperature and pressure. So this one's kind of tricky too because you have to figure out what the value for standard temperature is and the value for standard pressure. If you don't know those, you can look them up. There is an actual numerical value for standard temperature and pressure. So right there you have your standard temperature and your standard pressure. Like standard pressure is 101.3 kPa. And then you can look up your standard temperature, and then you have your P and your T, and you're solving for V. and here is your N. So that's how you're going to do that one. And then let me look at number 5 really quick, make sure nothing's going to trip you up. Volume, temperature, pressure. Ooh. This one right here, number 5. I'm just reading it again. Give me 1 second. I didn't read them ahead of time. I just read number 1 ahead of time. A sample of water vapor occupies. So we have a volume, a temperature, and a pressure. What volume, so you're looking for a volume, will the water vapor occupy when it's cooled? Here's a temperature, and the pressure remains constant. So there's a pressure. Look at the variables you have. You have volume, temperature, and pressure, and then you also have volume, temperature, and pressure. This is not a PV equals nRT. What is it? It's not a PV equals nRT. Which one of these gas laws have a pressure, volume, and temperature, and then another pressure, volume, and temperature? Oh yeah, combined gas law right there. So you're looking at your initial conditions and then your final conditions, and you're actually solving for V2 there. If you can't get number 5, let me know and I can help you through it. But I am going to sign off this video right now because it's getting really long. So if you need help with number 5, I'm going to write you a little note on it. This is combined gas laws. This is V1, T1, and P1. And then you're solving, this is V2, T2, and P2. And pressure and pressure. Actually, you don't even have to do that much, but it's okay. You can do a combined gas law here. But this is also 100.0 kPa, in case you were wondering. Pressure remains constant, so this could also be a Charles Law problem. It will work the same way. It doesn't really matter. So there you go. If you need help with number 5, let me know. But I really, 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 really think you can get this. I hope this video was helpful for you. I am putting away my calculator right now. It is 10:30 at night. I'm going to upload this video for you and then probably send out a remind. I do want to run through again. If you need any of these examples, and I've been scrolling through on this video, so it might have been hard for you to get a picture, but if you need any of this stuff, feel free to get on Class Kick. Here's the code. It is Chemoramma. I just made a new class, and it is the very first slide on there. I hope you guys have a really great night. I miss you a ton, and I hope to see you soon, maybe next year.